Next up, the next keynote is going to be about General Fusion and their engineering approach to delivering fusion energy. Please welcome Josh Nycholat, Manager, Investor Relations at General Fusion, to tell us about this.
All right, good morning, and thank you everyone for joining my presentation today. My name is Josh Nycholat. I'm Manager of Investor Relations at General Fusion. So for those of you who don't know, General Fusion is Canada's leading fusion technology development company. Since 2002, we've been pursuing a practical path to putting fusion energy on the grid called magnetized target fusion, and we've been building, operating, and testing machines that have advanced our technology step by step over the last few decades. We're at a really exciting time in our technology development phase right now because we have the world's first built and operating magnetized target fusion machine at our headquarters in Vancouver, and we're targeting key technical milestones with it over the next couple of years through the end of 2028. So with this machine, we hope to demonstrate 100% loss-in by the end of 2028, which is a significant scientific validation of our approach, magnetized target fusion, and I'll explain in the slides exactly how we do this. And because of all of this, and through the culmination of our efforts and where we're at with our technology and our science, we've decided we're going to enter the public markets. And essentially, we're going to be pursuing a SPAC merger with Spring Valley Acquisition Corporation. They're the same group that took companies like NuScale Power to public markets, and we think it's the right time to let the public markets participate in these milestones and in this technology development. So before I begin, let me just quickly remind you that this is for informational purposes only, make our lawyers happy here, and say that, it's just to tell you about General Fusion. So let me talk about our company at a glance. We were founded in 2002 by Canadian physicist Dr. Michel Laberge. He recognized that there's a significant gap in fusion and why fusion hasn't been commercialized to date, and that we need to think about how we address the challenges to commercializing fusion energy from the ground up, and we need to find an approach that can put practical electrons on the grid using existing technologies and existing materials wherever possible, to do this in a cost-effective way. We currently have 115 employees at our headquarters, and we've been backed by a group of leading institutional investors such as Temasek, GIC, and Jeff Bezos. And we have all of our efforts, test beds, and work to date has culminated into 210 patents that we maintain around the world and over 35 peer-reviewed publications on our technology. We've been featured in leading news around the world, and we currently have our LM26 machine operating in Vancouver at our headquarters. So for those of you who aren't too familiar with fusion, let me just start by explaining how it works. So fusion is the process that powers the sun and the stars. It's the nuclear process that our universe runs on. So essentially, it's where you're bringing two positively charged atoms under tremendous pressure and density and combining them to release energy. So we need to do that inside of a machine here on Earth because we don't have the gravity that the sun and the stars have to create this amount of energy and to create the force that we need to actually make fusion happen. So the two most common fuels that fusion uses to work are deuterium and tritium. They're two hydrogen isotopes. Deuterium is naturally occurring, and tritium needs to be produced through a number of ways. Essentially, we're taking deuterium and tritium fuels. We are under the right conditions, creating fusion with them, and through General Fusion's approach, we're capturing the energy using a proprietary liquid metal wall technology that I'll explain, and then we're converting that to put electricity on the grid through that liquid metal wall technology. So the four main barriers that fusion companies have faced to date when trying to commercialize fusion are up here on the screen. We have material degradation challenges, we have fuel sourcing challenges, energy capture challenges, and cost. General Fusion uses a liquid metal wall technology to address these challenges inherently. So the machine's liquid metal wall basically protects the machine from the fusion reaction. When deuterium-tritium fusion happens, neutrons are released, and we need to make sure that the first wall that they interact with can withstand the neutron bombardment. So we use liquid lithium, that when the neutrons travel through the liquid lithium, they interact with it, and they produce tritium fuel. That tritium fuel is produced at a ratio of greater than 1.5. Our partners at the UK Atomic Energy Authority have assessed that, and it's sufficient that we can repower the reaction and start up new fusion machines as well. The liquid metal wall also acts as a heat sink. It's essentially enabling us to create a hot liquid that we can then pump through a heat exchanger in our balance of plant plan that I'll show in a moment. And because we use all existing materials, or as many existing materials as possible, we can actually estimate a cost-competitive levelized cost of electricity in the $64 to $73 per megawatt hour range. So let me explain how our commercial machine will work, and then how our current machine, LM26, ties into that. So in our commercial design, we will have a large vessel. That vessel is a cylinder. We'll have an inventory of liquid metal inside of the machine, and we'll spin that vessel quite fast. When it spins, the liquid metal will be pushed up against the wall so that it's fully surrounding the chamber. And then we will inject our plasma, which is that deuterium-tritium fuel cloud, into the chamber, and we'll then collapse the liquid metal wall around the plasma. We're going to do this at 1 hertz. The way we collapse the wall is we have gas-driven pistons that push against it, first at the top and the bottom, so that we have a full spherical collapse around the liquid metal wall. We've tested the fluid dynamics of this collapse through one of our experiments, and we're confident that this design can achieve what we need to do with the liquid metal. Once the peak fusion happens, once the fusion happens at the center of the machine, the neutrons are released, as I mentioned, into the liquid metal. We produce the fuel, we heat it up, and then we can translate that to electricity on the grid. So general fusion has been working for a couple of decades on system-by-system de-risking core elements of our technology. We needed to check off several boxes to ensure that when we move forward to commercialization, or when we move forward to our next large integrated machine or a FOAK, that we're doing it in the most intentional way possible with the least amount of risk. So what we've done in all these test beds, there's been a couple of dozen, they've culminated into 3 main achievements and 3 main focus areas. First is plasma performance. With our technology, we need to produce a plasma because we're pulsing the approach and we're collapsing a liquid metal wall around it. We need to produce a plasma that lasts long enough to be mechanically compressed. That's core and essential for our technology to work. We've demonstrated that in over 200,000 plasma experiments at our headquarters, and we're confident that our plasma lasts long enough for mechanical compression. The next is liquid compression performance. We need to make sure that we can collapse a liquid wall with the right symmetry, that we can interact with the plasma, that it basically doesn't disrupt the plasma and make it go unstable. We've demonstrated this through a test bed called the cylindrical water compressor, and to test that cylinder to sphere collapse that we need. And the plasma compression. We needed to understand that when we mechanically compress a plasma, which is unique about our approach, that we can see neutron yield going up and to the right. We did a test bed in Vancouver called the PCS, and essentially we collapsed a small-scale plasma mechanically using force, and that actually, we saw the neutron yield that we expected. We published those results, and that gave us the intention and the validation that we needed to move forward to LM26. So LM26 was designed and assembled in December 2024 based off of all of these results. So in essence, we commissioned the machine and designed it, and what it's meant to do is to demonstrate that we can compress a plasma using a mechanical means in a way that can reach 100% loss in. So we believe that the dimensions of this machine are sufficient to do that. We achieved our first plasma in February of 2025, and we have then achieved our first plasma compression in April of 2025. Since then, we've been working on repeated plasma compressions to improve the performance of each shot. We're collecting the data and analyzing it, and we hope to achieve the following milestones on the bottom through the end of 2028. So the first being 1 keV, 10 keV, and 100% loss, and basically what that is increasing fusion yield up and to the right. And 100% loss-in is a significant milestone in our industry. It's basically a checkbox saying, yes, this technology is valid, and it's the scientific validation that we need to then move on to the next phase in our technology development path. So after LM26, we're going to work on a stage of our pathway called the demonstration of commercial systems. It's essentially the enabling technologies or the bells and whistles that we need to move from scientific validation to first-of-a-kind power plant. So because we're using that liquid metal wall in the rotating chamber that's that's compressed using pistons, we need to have things like seals and valves that can work with hot lithium. we need to have a heat exchanger that can interact with the hot lithium, and we need to work on our tritium extraction fuel cycle. We have some folks that are already working on these technologies around the world, but that's going to be our main focus at the next stage in our technology development path. And once we're towards the end of LM26, we'll begin working on that. Once that's done, we'll move on to a first-of-a-kind plant, which will basically be that first large-scale liquid compression that's producing either industrial heat or electricity. So we're targeting that to be operating by 2035, and the commercial systems will happen in between that. So we're here at this conference because we'd love to just connect with anyone who believes they could assist with any of the commercial systems program, and any companies that seem like they can work on those technologies, reach out to me on the app. I'd love to connect and discuss it. And the really big takeaway here is that General Fusion, through this Go Public transaction as well, has raised sufficient committed capital to complete the LM26 program. So that's essential to make sure that we can get through to that scientific validation milestone. We have a $108 million pipe that's already committed into that transaction, and that's going to take us through that Lawson milestone in 2028. So we're extremely excited about General Fusion. We're extremely excited about where we're going and the fact that the public markets are going to be able to participate. And we're really looking forward to seeing what's going to happen in the next couple of years. So thank you very much.